So the final speaker of this morning's session is Linus Nordberg, a software developer with a soft spot for security and network operations. After decades of experience with network-related development and operations, from working at Sunet, Nordinet, the Tor project, and as an independent consultant, Linus is now building security software for bare metal services. Please join me in welcoming Linus to the stage.
Thank you. Okay. Hi. Happy Pi Day. It's Pi Day today, 3.14, and we should have pie, I suppose, for dinner or for lunch. I'm between you and lunch. I know that, and I have a bit too much material, so I'm going to be quite quick, and we'll see if there's time before lunch. Maybe we can have a question-answer thing, and I can go back to stuff that you didn't catch. So, okay. Let's see. We're going to do it like this. I'm going to do a Tor crash course for those who haven't heard about Tor or don't understand some of the aspects. I'm going to give you a really quick overview of Tor and what it provides. And then we're going to talk about censorship circumvention, which is the main topic of the talk. And then we're going to do some sort of wrap-up. OK, how many in here have heard of Tor before? OK, that's almost all of you. Interesting. Please make a mental note of what your first association with this thing is, and we can come back at the end and see if I managed to change some of your assumptions on what it is and what it is not. We'll see. So how many of you who have heard of it have ever used it? I mean, have you ever used Tor? OK, that's not all of you, but maybe half of you. And how many of you have ever contributed to Tor by running a relay, running a bridge, or running a proxy? Wow, that's OK, nice. About 10 to 20 people. And how many of you are still running one of those things? Oh, nice. Thank you so much for providing the Tor network. Tor from a user perspective is a couple of things. And there are the common names at the right, and then there are my names at the left. So a less insecure version of the web. It's more known as onion services or hidden services. Some people even call it the dark web. Well, it is true that you can publish anonymously on onion services, but it is also true that you can do NAT punching, or it does NAT punching for you. So you can reach any onion server anywhere without that one having a public IP address. It is also the fact that onion addresses are self-authenticating addresses. So they are actually the pub key of the key pair that the holder of the service is the one that controls. So you have a cryptographical promise, or actually a real thing, that you are going to a site that if you have the right address, you will end up at the site, as opposed to the TLS version where you have a promise, more of a policy decision from a certification authority that says we're only going to sign certificates where this name is connected to that pub key. So this is more of a technical thing than a policy thing. The next thing is consensual authentication. You can choose when you identify. You don't have to walk around with your ID plastered on your forehead when you travel the internet. You can actually decide that, OK, I go over here, and then I present myself, rather than the current version of the internet where we spread our source and destination to all the routers between us and the destination. And this is probably the thing that Tor is more known for. This is the basic of Tor, where you can surf anonymously, basically. And then we have the main topic of this talk, which is internet access. You can actually be in a sensor area. You can sit in a network that is censored, and you can still reach the internet. So that's basically internet access. Why are we doing all this? Why are we caring about doing complicated stuff, and not just like go from source to destination? Well, there's this thing with metadata, and metadata is data about data, and IP headers is a good example because it is data that shows everyone who can see that, even if they can't see your payload because it's encrypted, they can see that someone is sending packets from here to there. And if we assume that a lot of actors on the internet today capture a lot of metadata and store it forever, we start to get a picture where we might want to care about this metadata. It is not only dangerous to assume that you are protected for everything in the future as well as today, just because you don't know what the metadata can be used for. So Tor is trying to give you a way of protecting your metadata against people who want to know more about you than you want. So Tor project provides two things: a network and a browser. It started out with a network. It's a TCP overlay network with a couple of thousands of relays relaying traffic over the ordinary internet. And then that gives you protection on layer 3, basically. But then it shows that there are many things above layer 3 that will also give your data away. In particular, the browsers, because they are kind of made for doing that. That is part of the business model, that the browser is supposed to tell some people about the things that you are doing. So Tor project is using a version of Firefox with some extra stuff in it. And a lot of these protecting things had, over the years, gone into upstream. So Firefox today is closer to what Tor browser was a couple of years ago than what it used to be. So that's really good. And the burden on the Tor project to keep this fork of Firefox is, of course, lower when we get more stuff into upstream. So far, so good. Okay, perfect. The overlay TCP network is a bit more complicated than just an overlay network. What it does is that if Alice wants to talk to Bob, she downloads the full list of all the relays in the network, containing also the public keys of all these relays. So when Alice wants to send stuff to Bob, she can start by encrypting each and every packet in 3 keys. So first she encrypts in the third hops. Okay, she starts by selecting 3. So this is source routed network, basically. She picks 3 relays, and then she encrypts in the third one, and in the key of the second one, and then finally in the key of the first one. She sends it off to the first hop, and the first hop can unwrap the outer package, send it to the second. The second can unwrap the second layer and send it to the third. The third can then send the unencrypted, from Tor's point of view, packet to the destination, like a website or Bob or whatever. And on the way back, you do the same thing, just reverse. So thanks to that, the third relay does know that someone is trying to talk to Bob, but they don't know where they come from. So they know the second relay, but they don't know the first one. Unless they are collaborating with the first one, it's impossible for them to correlate the data that Alice is talking to Bob. So that's the reason for the 3-hop solution. Compare that to a 1-hop solution that is more like known as a VPN. You have the problem that if someone is looking at the data at the VPN server or the 1-hop proxy thing, they can correlate, thanks to timing, who is talking to who and how much. And this is the metadata that we're trying to protect. And the other thing is that if you have a single point here, that can also be the target for blackmail or just breaking in or whatever. I mean, you have a single trust point here that you do not have in the large network with multiple hops. So who runs this network? There are 7,500 relays today. They are run by volunteers. So they are, by definition, not trusted. And that is also a reason why we want to separate first hop from third hop, because we cannot trust these relays, to be totally honest, not all of them. What we have to assume is that the large set of them, not all of them are dishonest, and not all of them are collaborating. So we have 7,500 relays. We want to have more, of course, because the distribution of the trust increases as the number increases, and as the diversity of these people, those who run these increases. And there are also some 2,000 or so unlisted relays. That's the red line down there. They're called bridges. They are unlisted in the sense that they are not in this public document that you can download, that Alice downloads in order to source route. And we'll talk more about this in a bit, because they are one of the basics for censorship circumvention. The size of the network is about 750 gigabits per second. That's the capacity. Is that much? Is that a lot? Or, I mean, in this crowd, in my view, it's kind of a lot, but of course it's not for you. But the interesting part maybe is the gap between what is the utilization and what is the capacity. And that has grown over the years. That is a 10-year graph, by the way. The other ones are 1-year graphs. But over 10 years, the gap between how much the network can provide and how much is utilized has grown, which means that you have a better service, basically. And this network is serving somewhere between 2 million and 8 million daily users. Now, users on the internet is hard to measure already as it is, but in an unlimited system it's even worse, because it is hard to count people if you do not track them, and we don't. So this is an estimate. It could be lower, it could be higher, but that's one of the estimates. It's also hard to know who are real users and who are bots and who are badly programmed stuff. So it's take it with a grain of salt, the number of users. So quick history of the project is that in the mid-90s, Paul Syverson at the US Naval Research Lab came up with the idea of onion routing, which is this 3-hop thing, and the encryption in 3 layers and decryption. Somewhere beginning in 2000, he found Roger Dingledine and Nick Mathewson, who started implementing this thing, and it got running somewhere. The first version got running somewhere early 2000. Mid-2000, the Tor project non-profit organization was set up, and since then it has grown and is today about 50 people, hired people, staff, and of course hundreds of people, volunteers doing programming, doing translations, or helping out and stuff like that, and obviously the many thousand volunteers running relays for the network. And all this costs money. So who's funding this? We are at about 50% US government money. And that has been a higher figure before. All of this is public data that you can find on the Tor website. Especially financials are very transparent in order to be able to explain to people why we're doing this, how we're doing this, and who is like behind this. Because lots of people are skeptical towards unlimited networks for a good reason. So we have to be very open and transparent with where the money comes from, who we work for. I mean, what are our goals? What is the process? How do we decide which features to do to work on and stuff like that? And about a third these days of the money comes from individual donations, thanks to a huge effort in the funding team, aka the money machine at Tor, that has been working super hard to try to bring down the dependency on one single source of revenue. So especially end of year is one of the times of year when you see some notes from them that ask you to donate a bit. And then we have on third row here is non-US governments, and that is actually equals Sweden. So Swedish SIDA is providing some funding for the past 15 years or so. Have we been doing that? So that's a good thing. Foundations clocking at 4, and then corporations are at 5, because corporations do not really care about this, obviously. Or they care at the tone of $200,000. This is 22, was the last thing I found. And corporations might want to improve their story here a bit, because also corporations too need a working internet. They need an internet that is safe for their users and is reachable for all the users on the internet. If they want to have value in their network, they should be reachable. Okay, that was a crash course. Are you still awake? Okay. That was a lot in a short time. I want to try to bring it down a bit when we come into the main topic of today. This is censorship circumvention. How do people get blocked? So there are basically three selectors. I'm not going to talk about how the exact blocking happened. I mean, it can happen by dropping some traffic. I mean, you can have filters on the path, dropping traffic that you want to drop, or you can have things on the side, shooting resets back to the source, or shooting resets to the target. There are plenty of ways. I'm not going to go into that today. I'm going to go into the selectors. So how do a sensor select what kind of traffic is supposed to be blocked by them? So destination address is an obvious one. If you know the address, you can. I mean, you have a list of all the proxy addresses, for example. If you have a list of all the relays of Tor, well, you do, because Tor is. I mean, that list is public. So Tor is very easily blocked on destination address, for example. The next thing you can do is you can look at protocol behavior. If you have an IDS system or something like that, you can look at what is passing through, and you can look at, okay, I don't like this one, or that protocol I don't care about. That protocol I cannot really afford blocking, which is one of the bases for censorship circumvention techniques today. You bet that no sensor wants to block everything, because you assume that there is some value to keep the internet working to some extent. So collateral damage is one of the terms that is being thrown around, and collateral freedom is the other word that people are using to try to describe how they try to look like something that their sensor is particularly keen on. So one sensor do not want to shut down HTTPS, but another sensor is fine with that, but they don't want to shut down WebRTC or something like that. So that's one of the things that you play on when you try to figure out how to subvert a sensor. And then the content, of course. If you have unencrypted traffic, you can just like, that was the old way of doing things. You had HTTP rather than HTTPS traffic, and China was usually dropping packets that contained a certain word, for example. And you simply drop that or kill that session, that HTTP session. And that is less common these days, but one can also argue that content and protocol behavior goes a bit together, and you can say that also destination address is, of course, a part of protocol. So this is not a perfect taxonomy, but it suits this discussion. Then there's a way for the sensor to improve the quality of their block list, basically, by reaching out to endpoints or to addresses that they think are proxies. So instead of just like blocking everything that they hear a rumor about being a proxy, they could do active probing. And this is kind of interesting for this audience, I think, because it has lots of Swedish connections. The first active probing that we heard of was from Leif Nixon. He was at some of the supercomputer centers, maybe in Linköping, back in 2010. And he saw strange things in his SSH logs. And he couldn't understand why these connections came, and he couldn't understand what the payload was. And it took some time, and after months, I think, he correlated these connections with legitimate SSH logins from users in China. And he puzzled it together that some part of the Great Firewall of China was doing some active probing to see if this SSH connection was strange in any way. And if it was, it could add it to the block list. And just a year later, Tor bridges started to become more quickly than before, blocked, and we didn't really understand why. And then puzzling this together with help from people from Karlstad University. This was Philip Winter and Stefan Lindskog, who published a great paper in 2012 about how China is blocking Tor. One of the results, or two of the results of that, was two obfuscation wire formats called scramble suit and obs4, which make the traffic look less interesting and also doesn't respond to active probing in a way. If the prober cannot prove that they have some sort of information, they will not get any response. So it's harder to do active probing on. Then a year later, more research came out of Princeton, Berkeley, and Karlstad again. And then it took 3 years before we saw any active probing that did not come from China. And that was Russia starting to do some probing. There is more in this, but I don't have the data here. But it is an interesting topic overall. If you are thinking of using censorship circumvention system or even designing one, think a bit about where do you leave your, what do you do with the traffic once you have reached through the sensor? Are you going to just like go to the destination, or are you going to go via an unlimited system? And I argue that you would like to drop your users into an unlimited system rather than going directly to the destination for a couple of reasons. First is, the more knowledge the sensor has about you and your traffic and your habits, the easier it's going to be to block you, if not today, then tomorrow. And the other thing is that you will probably not be able to connect to a trusted network outside of that. And even if many of you are running networks, so you might trust your network or not, it is hard to anticipate that is not going to be blocked at some point. If it has the common denominator, the sensor might find that and just block that wholesale. So most of the successful anti-censorship systems are run on a volunteer basis, because then you can have lots and lots of them, and they can be very, very diverse. So it's hard to find the pattern, and therefore hard to identify them as proxies. And of course, what is true today might not be true tomorrow. Things change over time, so be smart and do this stuff now, because assuming that people are storing, recording and storing metadata forever, and not only one, but multiple entities doing that, it might be a wise thing to actually do some protection even if you do not realize right now that you might be a target at some point. So I told you twice, I think, that it is really easy to block Tor, because the model is that a user downloads the full list of all the relays, and therefore any sensor can also download the full list of all the relays, and they do. And then they just add all those destination addresses to their filter, and then they're done. So the first thing that Tor did was to just don't publish all of your relays. So have a special set of relays that are not published. They are published in a specific way. So either they are not published at all, and if you set up a bridge, which is the name of this first entry that is non-public, you can of course send that IP address or that information that is needed to connect to it to your users. If you are an organization, you can send it in band, not publish it on the internet, because the challenge is your users need to find it, but the sensor must not find all of them. So either you have a high churn of these, so that it is hard for anyone to keep up. But essentially, it is a hard problem to distribute things to everyone and make sure that no one can get all of them. Tor is doing what it can. Tor is running a bridge distribution system for that. So all the bridges that are not marked as private, they go into this bridge distribution system, where we try to deliver 1, 2, or 3 addresses to you per time unit, say 24 hours. But we try to make sure that you cannot just like enumerate all of them. Well, when that doesn't work, for example, China is good at enumerating these things. Then adding a thing called a pluggable transport system was what happened in mid-2010, also say 2015 or something. It is basically a system where you can plug in a client and server component in the user Tor instance and in the bridge. And that is a program that you write, and you know best your sensor. So you know if your sensor is easily fooled by TLS-looking traffic or easily fooled by the other thing. If they want Skype, you make a Skype plugin. And people have made tons of these plugins, and they are easy to get into your existing system. You don't have to design it to be able to incorporate code in the Tor code base. And so Tor can just like keep working like before. And the pluggable transports that are most successful today, and those who are by default installed in the Tor browser when you download that, is OBS4. It stands for obfuscation, so that's a great name. It's really hard to pronounce as well. OBS4 is a look-like-nothing protocol. It looks totally random, and it doesn't respond to probes unless you have a key. The next one is Meek. That is another a tool in the toolbox of anti-censorship techniques. And it is called domain fronting. Is that a known thing, domain fronting? Okay, it's not super known. The idea is that a CDN, a content delivery network, has tons of sites behind their front. And they do some routing behind here. So you terminate a TLS session here, and then you route your traffic to the right web server somewhere over here. And so utilizing the fact that, for example, in TLS, you have the address in 3 different places, in different places in the stack, you could ask the front, the domain front, I want to go to something that is unblocked, something that a sensor has a hard time blocking because it's expensive, like Apple.com or Google's app engine or Azure or something like that. But once you come there and terminate the TLS traffic, you can have another host header in there. I mean, in the HTTP protocol, you have a host header. So the SNI, the server name indicator out here, is the thing that the sensor can see a block on. But once you have unwrapped or decrypted the TLS session, you can look at the host header and see, oh, they want to go over there, and that is the blocked site. So that worked fine for a long time, and then more and more of the large ones stopped supporting that. Google stopped in 2018 or 15 or something, and many of them are, I mean, Fastly quit their domain fronting 14 days ago, for example, which we'll see a bit later. And then we have Snowflake, which combines a couple of things. I will talk a bit more about Snowflake in 2 slides from here, so I'll leave it at that. The new contender is WebTunnel. It was released the day before yesterday, the International Day for Anti-Censorship on the Internet. And so that is the thing that looks like HPS. It's being pushed out by the Tor project right now, and we'll see if that is ever gonna be able to fight the other big ones. So today we have about 80,000 daily users using OBS4, about 35,000 on Snowflake, and the drop there is actually the Fastly. So Snowflake depends on domain fronting, and so that is when Fastly stopped supporting domain fronting. And then we have Meek as a low somewhere 10,000 maybe a day. And Snowflake is combining a couple of things. You have this censored user over there within the censored area, which is a red, yellow thing. They go to something called a broker. A broker is a single thing, using domain fronting to be able to be reached. So the client goes to the broker, and the client asks for a proxy. The broker looks at its set of numerous proxies, called Snowflake proxies, and picks one that they think that the client will be able to reach, considering all things. And the client goes connect there using WebRTC, betting that the sensor does not want to block WebRTC wholesale, because WebRTC is supposedly good for business, or it's an important protocol that you don't want to block based on just destination address. And the key here is that the Snowflake proxies are many. I mean, and they sit in all the networks. They sit in all the eyeball networks, and they sit in many places where the sensors cannot really pinpoint them and just like wholesale block them. Snowflake proxies are run, most of them are run as web extensions. So if you run Chrome or Firefox, I think, are the only ones, you can download this web extension, you just let it go, and then you can be the proxy for a sensor client. Snowflake has been most successful in Russia since late 21. So Russia started blocking for real, not when they invaded Ukraine, but rather 3 months earlier. So December 2021 was when we saw a huge drop in directly connecting Russians. And so Snowflake took a big jump when that started happening, and then Iran in mid 2022 with the uprising there. Then we had a huge influx of Snowflake users because Iran is not good at blocking Snowflake generally. And what the Snowflake proxy does then is sends it over to a bridge, and the bridge is a single or almost single machine. There are actually 2 of them carrying all the load from all the proxies. Some, I think, in total maybe 6, 7, 8, 9 gigabit per second, day and night. And then that one sends it to the destination. And the destination in this case is not where the user wanted to go. The destination is the second hop in the Tor connection. Because we don't want to let them directly to the destination. We want to protect the user from the people running the proxies and the people running the bridge. So therefore, we have hooked it into Tor, but Snowflake can be hooked into anything. So if you're running a VPN service, you can put Snowflake in front of your VPN so that you can have better success with letting people from India, for example, connecting. I hear India is throwing out all the VPN providers. If anyone wants to talk about India and VPN during lunch, I'm super interested. Okay, how are we doing on time? Okay, we're 10 minutes to lunch. I'm going to try to keep you for 10 minutes, and I'm going to let you go. So this is something where ISPs are the only ones who can help. And this is fairly new. It used to be called decoy routing some years ago. It has implementations called telex and tap dance and stuff like that. Nowadays, it seems to be refraction networking is the umbrella term for all these things. And the idea is that it's a bit like domain fronting, but not on the HTTP, HTTPS level, but rather on IPTCP. So usually, you ask an ISP to be part of this scheme where if they look at the traffic passing through their routers, they could divert, given a secret signal that only the client know, a secret signal saying that, okay, so I'm not actually going there, that the destination address in the header says, I'm actually want to go somewhere else. And so one of the implementations of that is especially interesting, I think, is Conjure. It is the latest one, and it has also been deployed in the largest setting I know of. I think they're running this on at least on a 20 gig router somewhere with 20 gig of traffic. I think this is Boulder, Colorado, that is doing this. So it is a passive, rather than the first versions, they were active, they were sitting on the traffic path, and that was not ideal. They lost some traffic that they actually wanted to get through. So now they have improved this a bit. So Conjure Station is totally passive, and it injects, when it sees the sign that someone wants to talk to something that is not actually the thing that it looks like, it injects, it hijacks that session basically and runs it towards the address that the user wants to go to, the blocked address. And it does that by utilizing non-used address space. So if you happen to have some address space that is not fully utilized, I mean, you might have lots of addresses and not all of them used. Maybe you can use some of those unused for this purpose. That's a great way to compensate for not using all the scarce resources. So, okay, we are getting close. What can network operators do to help people in censored areas? They can deploy Conjure. And I think it's quite a fun thing to do. I haven't done it yet. It's on my list. But I also do not have lots of address space. I have only a very small set of address. But if you want to do something about this, let me know, and I can get you in touch with the people developing this or trying to deploy it. Or we can just exchange notes as we go. You can support Snowflake. Help people run proxies. The number of Snowflake proxies is around 150,000. So 135 or 130,000 of these are people running just this web extension in their laptop. But A few thousand of them are standalone proxies. That's a program that you can just like apt install in your VPS, and then you can be more useful than you can be in your web browser, because you can carry more traffic. I mean, you can carry tens of megabits per second or even 100, but most of all, you're probably not under NAT restriction. So if you are not NATed, you will be reachable from inside. Most people running stuff on their laptops are probably NATed. So if the client is also NATed, you will have a hard time. You can do stun turn stuff, which that's what RDC does, but there are situations where that doesn't work. So if you want to help people run proxies in your network, give them a good deal on VPS or something, you can donate bandwidth hardware to, for example, these bridges. We need more of them. Or you can just donate money if you don't want to like do any work. You can just like throw some money on it. And please don't disconnect. I mean, lots of people want to help fight the bad people. So you want to be part of blocking or depeering these bad people, but think a bit about who is being hurt the most by you depeering this regime over there. Maybe the people under that regime need the internet to be able to understand that the regime isn't great. Okay, we are at wrap up. You still okay? Oh, good. We talked about what Tor provides and a little bit of how it works. We talked a little bit about what the selectors are, how you can think about how things are, or how people are getting blocked. I tried to explain why you want a unlimited system behind your great thing that towards the sensor. And I also tried to describe pluggable transports and bridges and the whole idea of that. And very, very short about refraction networking, which might be a fun thing for you to play with, and how you could help. And I think it's timely this year. This is the year, the super election year. At least half of the population of the world is voting for their parliaments. So not only the US and the EU, India, Iran, Russia, that's kind of a few important places. But there are more than that. I think Indonesia, which is huge. All of these people that are going to vote, they need information. They need good information. And they need to reach the internet in order to get that. And many regimes try to make their people not reach the internet because it's harder to control people who have freedom of information. So I think this is a great year to start doing this thing. And that's basically my pitch. Thanks for listening. And there are more reading here. You can download this presentation from that URL over there, and there all the links are in there if you don't want to like just photo and take up. So thank you.
Thank you very much, Linus. We have time for one quick question. If anyone has a burning thing on Tor they want to raise.
Thank you for a great presentation. I have actually two short questions. First question is, you mentioned that US government is sponsoring this project. What benefit does it have from that? And the second question is about, you also mentioned Russia and the spike of the Russian users. As you may know, from 1st of March, there's a new law in Russia which kind of not blocking VPNs, but you are not allowed to advertise VPNs. This is the first step. How hard is to block it on a governmental level or ISP level?
How hard is it to block?
Yeah. So in case,
or
yeah, Tor.
General. Okay. Yeah. Okay. So the first thing, the U.S. government wants an open internet. They want people in Iran and Russia to be able to get to the internet. Part of it used to be. Called BBG, one of the big funders of Tor. It's one of the things under State Department that also used to run things like Radio Free Europe, Radio Free Asia, those things. Like, how do we get information out to people in other parts of the world? So that is one of the arguments now for State Department to keep doing this. The reason they started this back in the mid-90s was because if we're going to use the internet and we're going to go around the world, we might not want to keep the US Navy here when we are walking into Baghdad or whatever. We might want to like lay low when we are in another country. How can we do that using the internet? So that was kind of the background of why they think this is needed. So the users of Tor is not only strange or dangerous or curious people, it is also lots of people in states are using this to be able to not keep their identity on their forehead when they go to the check in to the hotel and just like try to read their email from navy.mil. So that's two answers to why they want to do that. CIDA has a similar reason, that they want to also promote an open internet that is useful for everyone. The second question, how easy is it to block Tor in Russia or anywhere? Well, that's easy. And that's why we have all these anti-censorship ideas and protocols that we try to move forward. And we try to move quicker than the censors. It is a bit rough because they have lots of resources. We have, as you saw, we have a staff of 50 and we have a revenue of a couple of million US dollars yearly. So that's why we also try to send people to these places and ask for help, because we cannot really do this alone. So blocking Tor is easy. We try to come up with ways of not making that easy. And in the case of Russia, what happened first March, I think, was that they required that if you run a VPN service, you will have to register, and then you will have to provide some data to the authorities. That is, by the way, the exact same thing that happened in India some, was it weeks or months ago? So many of the VPN providers that I know of are pulling out of India now because they don't want to operate under that circumstance. And therefore, the only people that can run, and that's the same for Iran since many, many years. The only VPNs that can operate are sanctioned by the government. And the government is only giving sanctions to those who, cooperate. And so I think that that's also a good reason for trying to find other ways of getting out of censored areas. Thanks.
Okay, great. If you have any other questions, please grab Linus in the lunch break.
Yeah.
But for now, please join me in thanking Linus for a fantastic presentation.
Thanks.